Howdy, class. Once again, just Noah Housley. I'm just doing this for my own study, but maybe it can benefit you guys as well. I wanted to talk about one of the practice problems in the book. This is sample problem 11.5 with the elevator and the ball and practicing kinematic equations. So let's just get in. I'll read the problem. The problem states in an elevator shaft. So we have an elevator shaft here. A ball is thrown vertically upward with an initial velocity of 18 meters per second and thrown at v. And from a height of 12 meters, so x naught. At the same instant, an open platform elevator passes the 5-meter level, right there, moving upward with a constant velocity of 2 meters per second. 2 meters per second. Determine, first, when and where the ball hits the elevator, and the relative velocity of ball with respect to elevator. In other words, they want t and x where they meet, and then the relative velocity when they meet. Okay, so let's talk about what does this kind of mean. So we have this ball thrown up, and let's just throw the path of, let's draw the path of a normal ball, no elevator. A normal ball thrown up would go like this, and then back down. And so now let's put an elevator in there. So an elevator is coming up like this, and it'll continue to go up. Ooh. So it's asking at what point on these two paths do they intersect? So if I were to draw this in the graph, I should really just draw that part since it's time and there's no negative time. We have the ball, that is a parabola, give or take, and a elevator that is a straight line because of the constant velocity. So it's basically saying, where is this? Now that we've drawn it on a graph, in high school we'd see something like this and we'd go, systems of operations. Meaning that some equation quadratic, so a squared plus bx plus ax squared plus bx plus c is equal to mx plus b. And we'd solve for that. And so that's what we have here. So why can't we do that? Fact is, we are going to do that. So the two equations we're going to use in this problem are v, or v final, is going to equal v naught, v initial plus at, and x position is going to equal initial position x naught plus initial velocity v naught times t plus 1/2 at squared. A reminder that a is going to be negative, because at least I'm calling it negative in this problem. I thought it made things easier. So let's solve. So first, let's take the two equations of their position. And we're going to do what we thought of here. We're just going to solve a system's equation, have them equal to each other. And so my x for one problem is going to be x naught. So let's do the ball first. X naught started at 12 meters. And then it's going up at a velocity of 18 meters per second. That was the v naught. And we're multiplying that by time. Then we're going to minus a 9.81 over 2. That's a. And then over 2 the 1/2. And that's going to be times t squared. This, since we're doing the system equations, equals, there's a little hair in my pen, the same equation, but for position now. So for position, x naught, it started at 5 meters. And it's going up at 2 meters per second. We're going to multiply by that time. It's at a constant velocity, so that goes away. So there's no acceleration there. Now we solve this. I'm going to minus that over, and I'm going to minus that over. So I have a quadratic to solve. 7 meters plus 16 meters per second times t minus 9.81 over 2 times t squared. I have the quadratic, and this probably can't factor nicely, so I'm just going to skip to the quadratic equation. So b is 16, so I have negative b plus or minus square root b squared minus 4 times a, which is negative 9.81 over 2, times c, which is 7, all over 2a, which is negative 9.81. When you solve this, you get two answers, and since it's time, only the positive answer makes sense, so that comes out to be 3.65 seconds. Good. Now we've solved the when. Check. Now we need the where. Well, that's easy since we have both the position equations. Now we just plug in time. And this one's shorter, so I'm going to do that one. And that comes out to be 12.3 meters. Okay. Now, I'm running out of room here. I'll just go to the next page. Remember what we wanted. We wanted relative velocity. So I'm going to bring this over to the next page, which is velocity of the ball minus the velocity of the elevator. So we want the relative velocity. So I'm going to use the equation v equals vi plus at in this equation. So the velocity of the elevator is constant. We know that. So that's 2 meters per second. Velocity of the ball changes because there's gravity acting on it. So that's more of an equation. And so if we use this equation here, we have 18 and then minus 9.81 times t. And so that's our equation for the ball. So I'm going to put that there, and I'm going to combine them two, and I'm going to make it 18 minus 9.81 t minus 2. Combine 16 minus 9.81 t is equal to relative velocity, VR, or virtual reality. Whoa. Okay, now this is when they combine, so plug in a 3.65 seconds there. That comes out to be at negative 19.81 meters per second. Now let's talk about our answers here. Negative. What does that mean? That means that if I'm going to draw a point view. If I'm in an elevator and I'm looking out of the, awkward. I'm looking out on the elevator. So I see the wall passing through like that. This is the door of the elevator. I'm looking out. That means that I see a ball go down at negative 19.81 meters per second. That's what that negative means. That it's relatively going down at that speed. And that's what that means. Okay, this is, again, sample problem 11.5. Hope it helped. Thank you for watching.